What if I told you that right now, at this very second, someone from the future might be watching us silently observing, taking notes, maybe even laughing at how little we understand about time? It's a dizzying thought, but it's just one of the countless mind-bending possibilities that come with time travel. Think about the grandfather paradox, where a time traveler goes back and accidentally prevents their own birth. Or the bootstrap paradox, where an object or piece of information loops endlessly with no origin. These aren't just plot twists from your favorite sci-fi movies. They're real dilemmas that physicists and philosophers grapple with when trying to unravel the secrets of time. For centuries, the idea of moving through time like we move through space has captivated humanity. From H.G. Wells' The Time Machine to blockbuster films like Back to the Future, the concept feels just tantalizingly out of reach. But what if it's not purely fiction? What if the laws of physics, the fabric of the universe, actually allow for it? That's where things get thrilling. Across the globe, scientists and theorists have proposed not one or two, but 30 compelling theories that could explain how time travel might work. Some hinge on bending spacetime with massive gravitational fields. Others suggest weaving through microscopic wormholes or riding cosmic strings like elevators through the ages. And then there are the wildcard ideas like quantum entanglement, creating shortcuts through time, or parallel universes branching off with every decision we make. Today, we're going to explore all of them. Whether you're a skeptic who thinks time travel is pure fantasy or a believer convinced we're on the brink of cracking the code, this journey will stretch your imagination. We'll dive into black holes, twist through wormholes, and even question whether time itself is as fixed as we think. Along the way, you'll discover why some of the brightest minds in physics argue that time travel isn't just possible, it might already be happening. So buckle up. By the end of this, you might never look at a clock the same way again. Einstein shattered our everyday understanding of time when he revealed it wasn't a rigid, unchanging force. It bends, stretches, and even slows down depending on where you are and how fast you're moving. His theory of special relativity showed that the closer you travel to the speed of light, the more time distorts around you. Picture two identical clocks. One stays on Earth while the other rockets through space at nearly light speed. When the traveling clock returns, it's lagging behind not because it's broken, but because time itself passed slower for it. This isn't just theoretical. Astronauts on the International Space Station experience it firsthand, aging microseconds less than people on the ground due to their high orbital velocity. But things get even stranger with general relativity, which introduces gravity's role in warping time. Imagine standing near a black hole where gravity is so intense that light barely escapes. Time there would crawl compared to somewhere far away in the cosmos. You could orbit the black hole for what feels like minutes, only to return to Earth and find decades have passed. This gravitational time dilation isn't science fiction. It's built into the tech we use every day. GPS satellites orbit high enough that Earth's gravity weakens slightly for them, causing their onboard clocks to tick faster than ground-based ones. If engineers didn't account for this, your navigation apps would misplace you by miles within minutes. What's truly wild is that relativity doesn't just permit time travel to the future, it practically demands it. The twin paradox illustrates this. If one twin zooms off on a near light-speed journey and returns, they'll be younger than their Earth-bound sibling. No paradoxes, no breaking physics, just the universe enforcing its rules with eerie precision. Of course, traveling backward in time is trickier, but relativity leaves the door cracked open for possibilities we're only beginning to explore. The universe, it seems, is far more flexible with time than we ever dared to dream. If black holes twist time like a cosmic whirlpool, wormholes could be the secret tunnels that let us hop across it. Picture spacetime as a vast sheet of paper. Fold two distant corners together, and a wormhole would be the needle punching straight through, creating a shortcut between them. The concept was first seriously explored by physicist Kip Thorne in the 1980s, sparked by a question from his friend Carl Sagan, who wanted a scientifically plausible way to transport characters in his novel Contact. Thorne realized that according to Einstein's equations, wormholes, technically called Einstein-Rosen bridges, might not just be possible but could act as time machines if stabilized. Here's the catch: wormholes, if they exist, would snap shut instantly under the crushing weight of their own gravity, unless held open by something truly bizarre: exotic matter. Not antimatter, not dark matter, but matter with negative energy density, which bizarrely exerts a kind of antigravity, pushing spacetime outward to keep the tunnel from collapsing. No one's ever found exotic matter, and it might defy known physics, but quantum mechanics hints that tiny amounts could theoretically exist in the form of Casimir vacuums or quantum fields. Even a gram of it might be enough to prop open a microscopic wormhole, though scaling up to human size would require amounts that sound like pure fantasy. The time travel potential gets wilder. If one end of a wormhole stayed on Earth while the other accelerated to near light speed, time dilation would kick in. Return the moving end to Earth after a year, and its clock might show only a day had passed. Step through, and you'd effectively walk into Earth's past. But don't pack your bags yet. Beyond exotic matter, there's the slight issue of radiation feedback. Any particle entering the wormhole could loop infinitely through it, building energy until the resulting explosion destroys the tunnel or the time traveler. Thorne himself later concluded that nature might forbid such paradoxes entirely, slamming the door on backward time travel. Yet some theorists still hold out hope, tweaking the math to find loopholes. Wormholes remain the ultimate cosmic what-if bridges to the stars or perhaps to yesterday. Closed timelike curves sound like something ripped straight from a physicist's wildest daydream, but they're very real mathematical solutions to Einstein's equations. Picture time as a winding river. Most of us float downstream, but CTCs are like hidden whirlpools that loop back on themselves, potentially carrying you to your own past. These bizarre pathways through spacetime don't just bend the rules, they twist them into knots, offering a way to revisit moments you've already lived without violating relativity. The idea first gained traction when legendary mathematician Kurt Gödel discovered that in a rotating universe, spacetime itself could curl into these cosmic corkscrews. His model described a cosmos spinning so uniformly that if you set off in a straight line long enough, you'd eventually return to your starting point, not just in space but in time. Gödel's universe might not match our own observations, show the cosmos isn't rotating globally, but the revelation cracked open a door. Suddenly, time travel wasn't just about wormholes or black holes. It could be baked into the fabric of reality under the right conditions. Fast forward to today, and physicists like Kip Thorne and Stephen Hawking have wrestled with CTCs, probing whether they could exist in pockets of our universe. One compelling scenario involves massive rotating cylinders. Imagine a neutron star stretched into an infinite spinning rod. According to physicist Frank Tipler, such an object would drag spacetime around it like syrup on a spoon, creating a CTC where circling the cylinder could send you backward in time. But here's the catch: CTCs come with paradoxes that make physicists' heads spin. The infamous grandfather paradox becomes unavoidable. If you travel back and disrupt events that led to your existence, how could you ever have been born to make the trip in the first place? Some theories sidestep this by invoking quantum mechanics, suggesting alternate timelines branch off to absorb inconsistencies. Others, like Hawking's chronology protection conjecture, argue that nature outright forbids CTCs to prevent paradoxes, perhaps through quantum effects that collapse the curve before it forms. Yet intriguingly, recent experiments with quantum particles hint that tiny time loops might evade these restrictions, operating on scales so small they don't trigger paradoxes. Whether CTCs are cosmic glitches or nature's way of teasing us with possibilities we can't quite grasp, they remind us that time is far stranger than any clock could measure. Frank Tipler's cylinder sounds like something ripped from the pages of a sci-fi epic, a bizarre, infinitely long, ultra-dense rod spinning at mind-blowing speeds. Yet this wild idea isn't just fantasy. It's a serious theoretical proposal for how we might manipulate spacetime itself to crack open the possibility of time travel. Tipler, a physicist crunching Einstein's equations in the 1970s, discovered something astonishing. If you could build a cylinder with the mass of several suns compressed into an impossibly thin, endless structure and set it rotating at nearly the speed of light, the sheer drag of its spin would twist spacetime around it like taffy. Circling this cosmic whirligig in just the right path could, in theory, send you spiraling backward in time. The mechanics are dizzying but elegant. Imagine spacetime as a flowing river. Normally, we're all drifting downstream with the current of time, but Tipler's cylinder would create such a violent whirlpool in that river that paddling along its edges in precise loops could slingshot you upstream into the past. This isn't just metaphorical. The math shows closed time-like curves forming around the cylinder, offering a potential route to earlier moments. The catch: building one would require technology and materials so far beyond our grasp they border on magic. First, you'd need matter dense enough to rival a neutron star. Just a teaspoon would weigh billions of tons. Then there's the small issue of the cylinder needing to be infinite in length, since any finite version would unravel the delicate spacetime warping needed for time travel. Even if we somehow overcame those impossible hurdles, nature might still have the final say. Quantum effects or hidden laws of physics could destabilize the cylinder the moment it nears time warping speeds. Plus, navigating the trip would be lethally precise. Veer too close to the cylinder, and tidal forces would spaghettify you. Drift too far, and the time-bending effect vanishes. Yet for all its impracticality, the Tipler cylinder remains a fascinating thought experiment. It proves that within the rigid framework of general relativity, time travel isn't just possible, it's a puzzle waiting for the right pieces to fall into place. Until then, it stands as a towering what-if, reminding us that the universe's rulebook might still have chapters we haven't dared to read. Quantum mechanics throws everything we thought we knew about time into a blender, and what comes out is stranger than fiction. At the subatomic level, particles don't play by the same rules as the world we see. They exist in multiple states at once, a phenomenon called superposition, where an electron can spin both clockwise and counterclockwise until you measure it. But here's where it gets wild. This blurry, undecided state might be more than just a quirk of tiny particles. It could be a clue that time itself isn't as linear as we assume. Think of it like a movie reel where every possible frame exists simultaneously until the universe chooses one to project. The delayed choice quantum eraser experiment is a perfect example of how quantum mechanics laughs at our classical notions of cause and effect. In this mind-bending setup, scientists can seemingly change the past behavior of a particle after it's already been measured. Here's how it works. A photon is sent through a maze of mirrors and detectors, but the choice to observe its path or erase that information happens later. Somehow, the photon acts as if it knows whether its path will be recorded or erased, even though that decision occurs in its future. It's as if time loops back on itself, blurring the line between past and present. Quantum entanglement adds another layer of weirdness. When two particles become entangled, their properties sync up instantly, no matter how far apart they are, even across galaxies. Einstein called this spooky action at a distance, but it's real, and it suggests that information might bypass time entirely. Some theorists argue this could hint at a deeper, non-linear structure of time where cause and effect aren't set in stone. Imagine time as a vast network, not a straight line, where events influence each other in ways that defy our everyday logic. Could these quantum riddles be glimpses of a universe where time is more like a tapestry, woven with threads that twist and cross in ways we're only beginning to untangle? The math says it's possible, but until we find a way to scale these effects beyond the subatomic world, the mystery remains. One thing's for sure: if quantum mechanics holds the key to time travel, the universe is playing a far stranger game than we ever imagined. Stephen Hawking had a mischievous streak when it came to time travel. While he famously declared that the universe doesn't allow time travelers at parties, after throwing one and waiting in vain for guests from the future, his real contribution was far more profound: the chronology protection conjecture. It's essentially nature's cosmic safeguard, a theoretical rule that slams the brakes on backward time travel to prevent the universe from unraveling at the seams. Hawking's brilliant insight was that spacetime itself might have a built-in repair mechanism, patching up potential time loops before they could form. Think of it like an immune system for reality, where quantum fluctuations act as white blood cells attacking paradoxes before they infect the timeline. At the heart of this idea is a cosmic irony. While Einstein's equations permit closed timelike curves, the universe seems to go out of its way to block them. Hawking noticed something peculiar about the math. Whenever a time loop starts to take shape, quantum effects like vacuum fluctuations or radiation from black holes would theoretically flood the area with infinite energy, effectively shredding spacetime at the moment of formation. It's as if the universe has a fail-safe switch that fries the circuitry of any would-be time machine. Some physicists compare it to trying to balance a pencil perfectly on its tip. In theory, it's possible, but the tiniest vibration, or in this case quantum jitter, makes it collapse instantly. Yet the debate isn't settled. Recent advances in quantum gravity suggest loopholes, instances where microscopic time loops might briefly exist before nature corrects them. Experiments with entangled particles even hint that causality can bend without breaking on tiny scales. But Hawking's larger point remains haunting. If time travel were possible, why haven't we met a single tourist from the future? His conjecture offers a chilling answer, not because they're hiding, but because the universe simply won't let them arrive. Time's arrow, it seems, isn't just a metaphor. It might be law enforced by the cosmos itself. Multiverse theory offers one of the most elegant solutions to time travel's messiest problem paradoxes. Imagine stepping back in time and accidentally preventing your own birth. In a single, linear timeline, this creates an impossible loop. But what if every possible outcome plays out somewhere? That's the radical promise of the many worlds interpretation of quantum mechanics, where every decision, every chance event, splinters reality into infinite parallel universes. Under this model, time travel wouldn't rewrite history. It would simply spin off a new branch of reality, leaving the original timeline untouched. Think of it like a choose-your-own-adventure book where every possible choice leads to a fresh page. If you traveled to the past and altered an event, the universe wouldn't unravel instead. It would fork into two streams, one where you never intervened, and another where your actions ripple forward into a brand new timeline. This sidesteps the grandfather paradox entirely. Even if you erased your own ancestry in the new branch, the original version of you would still exist in the universe you left behind. The math behind this is rooted in quantum superposition, where particles exist in multiple states until observed. Applied to time travel, it suggests every possible outcome must happen, just in different worlds. Some physicists take this further, proposing that wormholes or black holes could act as bridges between these alternate realities. A hypothetical time machine might not send you backward in your own timeline, but shunt you into a parallel universe where history unfolded slightly differently. Picture arriving in a 1960s where the Cuban Missile Crisis escalated into nuclear war, or a 22nd century where humanity never left Earth. These aren't just hypothetical. String theory suggests our universe could be one bubble in an endless foam of multiverses. each with its own unique physics and history. Yet the multiverse idea isn't without its critics. For one, it's untestable by nature. If alternate realities are forever out of reach, how could we ever prove they exist? Others argue it's a philosophical cop-out, swapping paradoxes for infinite, unobservable universes. But for those wrestling with time travel's logical knots, the many worlds interpretation offers something priceless, a universe where the rules don't break, they just multiply. Whether it's science or sophisticated fiction, one thing's certain: if time travel is real, the multiverse might be the only way to keep reality from tearing itself apart. What if bending spacetime itself could become our shortcut through the cosmos? That's the radical promise of the Alcubierre drive, a theoretical warp engine dreamed up by physicist Miguel Alcubierre in 1994. Instead of moving a ship through space at impossible speeds, this concept cheats the universe's speed limit by compressing spacetime in front of the vessel while expanding it behind, effectively surfing a wave of warped reality. Picture a surfer riding a tidal wave. The water itself carries them forward while they barely move relative to the wave. The Alcubierre drive would do the same with the fabric of spacetime, creating a bubble where the ship sits motionless inside while the universe folds around it. Einstein's laws say nothing can outrun light within spacetime, but they never said spacetime itself couldn't move faster. The catch: this cosmic loophole demands staggering amounts of energy. Early calculations suggested the drive would require the equivalent of Jupiter's entire mass converted into pure energy, clearly beyond our reach. But recent refinements hint at slimmer possibilities. By tweaking the shape of the warp bubble, making it thicker or oscillating, some theorists argue the energy could shrink to the mass of a small moon. There's even wilder speculation about harnessing exotic matter or manipulating dark energy, the mysterious force accelerating the universe's expansion. For now, these are just equations on paper, but they reveal a tantalizing truth. Physics might not forbid faster than light travel after all, yet the hurdles don't stop at energy. Creating a warp bubble would unleash tidal forces strong enough to vaporize anything near its edges. There's also the unsettling possibility that particles caught in the bubble's walls would accumulate infinite energy, triggering cataclysmic explosions upon arrival. And then there's the question of control. How would you steer or stop a warp bubble once it's formed? Alcubierre himself admits his idea is more mathematical curiosity than blueprint, but it sparked serious research at NASA's Advanced Propulsion Physics Lab, where scientists toy with microscopic warp field experiments. The most mind-bending twist: the Alcubierre drive could technically enable time travel. According to relativity, arriving faster than light means arriving before you left, essentially jumping into the past. This turns a hypothetical starship into a de facto time machine, where a round trip to Proxima Centauri might return you to Earth centuries before departure. Suddenly, warp drive isn't just about reaching the stars, it's about unraveling time itself. While we're light years from bending spacetime at will, the mere fact that such ideas survive scientific scrutiny proves how fluid the cosmos might truly be. Time crystals sound like something straight out of a wizard's lab, but they're very real, and they might hold clues to one of physics' greatest mysteries: how to manipulate time itself. Unlike ordinary crystals, where atoms arrange in repeating patterns in space, think the hexagonal lattice of a snowflake. Time crystals are structures that repeat in time. Imagine a clock that ticks forever without any energy input, a system that perpetually cycles between states like an endless dance frozen in the fabric of reality. This bizarre behavior defies our usual understanding of thermodynamics, where systems eventually settle into equilibrium. Time crystals don't. They're the first known example of non-equilibrium matter, a new phase of existence that keeps moving even when it shouldn't. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, met initially with skepticism. Critics argued it violated fundamental laws. How could something oscillate indefinitely without energy? But by 2017, two separate teams of scientists had created time crystals in the lab, using chains of charged atoms chilled to near absolute zero and manipulated with laser pulses. The result, atoms flipping their spin states back and forth in a rhythmic, time-repeating pattern, like a metronome ticking without being wound. The breakthrough was so significant it landed on Physics World's list of the year's top discoveries. What makes time crystals tantalizing for time travel research is their relationship with temporal symmetry breaking. Normally, the laws of physics work the same whether time runs forward or backward, a principle called time symmetry. But time crystals spontaneously break this symmetry, choosing a preferred rhythm in time, much like magnets break spatial symmetry by aligning their poles. Some theorists speculate this could hint at ways to engineer systems where time's flow isn't uniform, where pockets of reality might tick at different rates or even loop. Picture a time cage where local seconds stretch into outside hours, or a device that lets you step outside linear time momentarily. Of course, we're far from building a time machine from time crystals. Current versions exist only in ultra-controlled quantum systems and last mere fractions of a second, but the implications are staggering. If we could scale them up, might they act as cosmic clocks for wormhole stabilization or as components in a quantum time loop processor? Could they help us simulate closed timelike curves in the lab? For now, these questions hover at the edge of science fiction, but so did lasers and transistors once. Time crystals remind us that the universe still has tricks up its sleeve, and the key to time travel might not be bending space, but rewriting time's rhythm from the inside out. Black holes aren't just cosmic vacuum cleaners, they're potential time machines, and the key lies in their spin. A rotating black hole, known as a Kerr black hole after physicist Roy Kerr, who first solved Einstein's equations for them, warps spacetime so violently that it drags the very fabric of reality around it like a whirlpool in molasses. Unlike their static counterparts, these spinning monstrosities have a hidden feature, an ergosphere, a region outside the event horizon where space itself is forced to rotate with the black hole. Step inside this zone and you might find an escape route, not just from the hole but from your own timeline. The real magic happens deeper inside, past the event horizon of a Kerr black hole. Theoretical models suggest the singularity isn't a point but a ring, a gateway where the crushing gravity might momentarily invert. If you could navigate this labyrinth of twisted spacetime with perfect precision, some calculations show you might pass through the ring's center into a wormhole-like region, emerging in another time or even another universe. It's like threading a needle through the eye of a cosmic storm, where the wrong move means being shredded into atoms, but success could rewrite your personal clock. But let's be clear, this isn't a joyride. The tidal forces near a black hole would stretch you into a human noodle, a process called spaghettification, long before you reach the theoretical time-bending zone. Even if you survived that, the radiation near the singularity would cook you faster than a supernova. And here's the cruel twist. While Kerr black holes mathematically permit time travel, they're horrifically unstable. The moment anything, even a single photon, tries to pass through the ring singularity, most models predict the wormhole would collapse, sealing your fate mid-journey. Yet the tantalizing possibility remains. If a civilization could somehow stabilize the black hole, perhaps by injecting negative energy or manipulating quantum fields, they might turn the universe's most destructive objects into temporal highways. Until then, these spinning behemoths stand as both a warning and a promise. Time travel might be written into the laws of physics, but the universe makes you earn every second. Cosmic strings are some of the most exotic and elusive structures the universe might harbor. Picture spacetime not as a smooth fabric, but as a quilt with flaws woven into its very structure during the Big Bang's violent birth pangs. These flaws, stretched thinner than a proton across light years of space, would carry unimaginable density, just a single inch of cosmic string could outweigh Mount Everest. Their gravitational pull is so intense that they don't just bend spacetime, they slice through it like a scalpel, leaving sharp creases where the rules of physics twist in their wake. And if two of these strings were to cross paths or vibrate in just the right way, they could stitch closed time-like curves into the universe's fabric, creating loops where time folds back on itself. The mechanics are as elegant as they are bizarre. When cosmic strings interact, their immense gravitational fields warp spacetime so severely that parallel world lines, the paths objects take through time, can knot together. Imagine two strings whipping past each other at near light speed. The spacetime between them would contract so violently that a spacecraft circling the pair could, in theory, return before it left. It's like running laps around a twisted racetrack where the finish line somehow appears before the starting gun. Physicist J. Richard Gott, who pioneered this idea in the 1990s, showed mathematically that such a setup wouldn't just allow time travel, it would demand it, given relativity's rules. But there's a catch. Cosmic strings, if they exist, are nearly impossible to spot. Unlike black holes, they don't swallow light. They merely distort its path, leaving faint gravitational imprints. Astronomers search for them by looking for telltale double images of distant galaxies, where a string's gravity acts like a lens splitting the light. Others hunt for sudden bursts of gravitational waves, the ripples that might erupt if a string snaps or collides with another. Yet after decades of searching, no definitive evidence has surfaced. Some theories suggest strings could have decayed moments after the Big Bang, vanishing before galaxies even formed. Others propose they're hiding in plain sight, their signals drowned out by cosmic noise. Even if we found them, harnessing cosmic strings for time travel would require engineering on a godlike scale. You'd need to locate two strings moving at relativistic speeds in perfect alignment, a cosmic needle in a haystack search. Then navigate gravitational forces that could rip planets apart. And there's the thorny issue of quantum effects potentially destabilizing the time loop before completion. But as a thought experiment, cosmic strings reveal something profound. The universe may be littered with natural time machines, remnants of its fiery infancy, waiting for a civilization clever enough to read the stitches in spacetime's fabric. Imagine a particle that doesn't just break the speed limit of the universe it was born speeding, forever outpacing light itself. That's the eerie premise of tachyons, hypothetical particles predicted by relativity that always travel faster than light. Unlike ordinary matter, which needs infinite energy to reach light speed, tachyons would require infinite energy to slow down to it. But here's where the plot twists. According to Einstein's equations, anything moving faster than light would experience time in reverse from our perspective. A tachyon streaking across the cosmos might vanish before it appears, arrive before it leaves, and effect before cause, a living, breathing grandfather paradox in particle form. The idea emerged in the 1960s when physicists realized relativity doesn't explicitly forbid faster-than-light particles, it just makes them behave bizarrely. Tachyons would have imaginary mass, a mathematical quirk where their mass squared is negative. While that sounds like nonsense in quantum field theory, it implies these particles could tunnel through spacetime in ways that defy classical logic. If they exist, they'd leave trails of Cherenkov radiation, a luminous shockwave akin to a sonic boom, but with light even in a vacuum. Scientists have hunted for these traces in particle accelerators and cosmic ray data for decades, yet every experiment has come up empty. The absence is so glaring that some argue it's evidence tachyons simply can't exist without unraveling causality itself. The paradoxes they spawn are mind-melting. Consider a tachyon beam fired at a detector. From the detector's perspective, the particle might hit before the gun is triggered, effectively allowing the future to alter the past. This isn't just a technicality, it's a direct violation of cause and effect, the glue holding reality together. quantum field theorists have proposed workarounds like tachyons being inherently undetectable or their signals always appearing as noise. Others suggest they might only interact with gravity, weaving through the cosmos unseen except by the faintest distortions in spacetime. Then there's the most radical idea that tachyons aren't particles at all, but glitches in the universe's code. Some models in string theory describe them as instabilities in spacetime's underlying fields, bubbles of false vacuum where the laws of physics temporarily short-circuit. If true, they wouldn't just be time travelers, they'd be fragments of a reality where time's arrow points in every direction at once. For now, tachyons remain ghosts in the equations, a tantalizing what if that challenges our deepest assumptions about time, causality, and the very fabric of existence. Whether they're out there, dancing just beyond the edge of perception, or merely mathematical phantoms, one thing's certain: the universe has stranger secrets than we've dared to dream. What if the universe has a built-in editor, ensuring every time travel story aligns perfectly with the past, no plot holes, no contradictions, no paradoxes? That's the spine of the Novikov self-consistency principle, a bold idea from Russian physicist Igor Novikov asserting that any actions taken by a time traveler were always part of history. Think of it like a cosmic rulebook. If you travel to the past, your presence there can't change anything because it already happened. The universe won't allow paradoxes, it smooths them out before they can form. This isn't just abstract theorizing. Consider the predestination paradox, where a time traveler's actions inadvertently cause the very event they were trying to prevent. Imagine going back to stop the assassination of a famous leader, only to accidentally bump into the killer's arm, redirecting their aim to ensure the fatal shot. Your attempt to rewrite history was history all along. Novikov's principle takes this further, arguing that such loops aren't just possible, they're inevitable. The universe would conspire to make sure your time meddling fits seamlessly into the timeline, like a jigsaw piece that only slots in one way. The implications are both comforting and eerie. On one hand, it sidesteps the messy grandfather paradox. You couldn't erase your own ancestry because you're proof it didn't happen. On the other, it suggests free might be an illusion when time travel's involved. Every choice you make in the past would already be baked into the timeline, leaving you more like an actor reading lines than a director rewriting the script. Some physicists compare it to a river flowing around a rock. The water adjusts its path, but the rock was always there. But how would the universe enforce this consistency? Quantum mechanics offers a clue. At the microscopic level, particles exist in probabilities until observed. Novikov speculated that quantum effects might correct deviations in a time loop, steering events toward the only outcome that doesn't break causality. Picture rolling a die in the past. No matter how many times you throw it, it lands on the number that aligns with the future you remember. The math even shows that in closed timelike curves, probabilities funnel toward self-consistent solutions, as if reality has a bias against paradoxes. Critics argue this feels suspiciously like fate dressed up in physics equations. If time travel were possible, why wouldn't the universe allow branching timelines or minor tweaks? And what about tiny inconsistencies like a time traveler leaving a fingerprint in the wrong era? Novikov's answer is razor sharp. Those fingerprints were there the whole time, unnoticed until now. The principle doesn't just protect causality. It reshapes our understanding of it, suggesting that time might be less like a river and more like a sculpture, every detail fixed, waiting to be observed from the right angle. For all its elegance, the self-consistency principle leaves one haunting question. If time travelers are among us, how would we know? The answer might be hiding in plain sight. Those inexplicable historical coincidences, the strokes of luck that seem too perfect, the moments where everything aligned just a little too neatly. Novikov's universe doesn't need to hide time travelers. It's already written their stories into ours. The holographic principle turns our entire understanding of reality inside out. What if the three-dimensional universe we experience is just a projection, a cosmic illusion encoded on a two-dimensional surface at the edge of space? It's a radical idea born from black hole physics, where scientists discovered that all the information swallowed by a black hole isn't lost but smeared across its event horizon like data on a celestial hard drive. Extend this to the entire cosmos, and suddenly, time itself might not be a fundamental force but a layer of information painted onto the universe's underlying code. Think of it like a movie. What we perceive as time, the flow of events from past to future, could be akin to frames flashing across a screen, while the real film exists as static images on a two-dimensional reel. Manipulate those images and you could rewrite the movie. Some physicists speculate that if the holographic principle holds, tampering with this underlying data might allow us to edit time's fabric, not by bending spacetime with gravity, but by accessing the universe's source code. Imagine a futuristic device that doesn't move you through time but reprograms your position in it, like dragging a slider on a video timeline. The mechanics get wilder when you consider quantum entanglement's role. If particles on the universe's theoretical 2D boundary are entangled with those in our 3D reality, changing one could instantly alter the other, a potential backdoor for time adjustments. Picture a cosmic glitch where tweaking data on the boundary layer shifts events in our world, creating ripples that look like time travel from the inside. Experiments in quantum gravity already hint at this possibility, with models showing how entangled qubits can simulate spacetime distortions in lab-scale holograms. But here's the catch: even if the universe is a hologram, cracking its encryption would require understanding physics beyond our current grasp. We'd need to locate the screen where reality is projected, likely at the cosmological horizon, billions of light years away, and decode its language. Some theorists propose advanced civilizations might harness black holes as natural supercomputers, using their event horizons to process temporal data. Others warn that meddling with the hologram's code could unravel causality entirely, turning time into a fragmented mess of contradictory events. Yet the principle offers a tantalizing clue. If time is information, maybe it's not a river but a dataset, one we might learn to rewrite. Until then, the holographic universe stands as both a map and a mystery, hinting that the key to time travel isn't out there in the stars, but etched onto the boundary of everything we know. What if time isn't a fundamental part of the universe at all, just a side effect, an illusion emerging from something deeper? That's the radical proposition of loop quantum gravity, a cutting-edge theory that suggests time might be as real as the sensation of moving when you're sitting on a parked train and the one beside you starts rolling. In this framework, the smooth flow of seconds we experience could be a cosmic sleight of hand, stitched together from discrete, indivisible chunks of spacetime at the tiniest scales imaginable. Picture reality as a film strip where each frame is frozen, but when played rapidly, our brains perceive motion. Loop quantum gravity argues that time works the same way, a flickering sequence of quantum moments so fleeting they trick us into feeling continuity. This rewrites the rules for time travel entirely. If time isn't a river but a series of snapshots, moving through it wouldn't mean warping spacetime. It'd mean hopping between those frozen frames. Think of it like flipping through a graphic novel. Normally, you read panel to panel, but if you could grab pages out of order, you'd effectively jump ahead or back in the story. The catch: these quantum leaps would happen at the Planck scale, trillions of times shorter than the blink of an eye, making human-scale time travel seem impossible. But some theorists propose that under extreme conditions, like near a black hole's singularity, these microscopic jumps could amplify, creating gaps where entire sequences of time detach and reconnect in new configurations. The implications are staggering. If time is emergent, paradoxes might not just be avoidable, they could be meaningless. In a universe where cause and effect are illusions, changing the past wouldn't create contradictions because there's no linear past to change, just a web of quantum correlations. You couldn't erase your own existence any more than a single pixel could delete the movie it's part of. This aligns eerily with quantum experiments where particles seem to retroactively influence their own histories, as if the universe is constantly editing itself to maintain consistency. But here's the twist: if time isn't real, why does it feel so inescapable? Loop quantum gravity suggests it's a collective hallucination, a side effect of entropy and quantum entanglement creating an arrow of time at larger scales. Like a crowd doing the wave in a stadium, trillions of quantum interactions give rise to the illusion of forward motion. Disrupt those interactions and the wave collapses. Hypothetically, a device that could decouple quantum states from this network might freeze local time or even reverse it, like running the stadium wave backward. Critics argue this reduces time travel to a philosophical quirk. If time isn't fundamental, traveling through it is like digging through the holes in a net. Yet the math holds tantalizing possibilities. Some models in loop quantum cosmology show that the Big Bang might not have been the beginning but a rebound from a previous universe's collapse, with time flickering in and out of existence like a cosmic light bulb. If true, our entire timeline could be one page in an infinite flipbook where time travel is just turning to a different leaf. Whether time is real or not, the universe has a cruel joke waiting. If it's all an illusion, breaking free might require rewriting the very rules of perception. And if it's fundamental, we're stuck wrestling with paradoxes. Either way, the answer lies not in machines or wormholes, but in the quantum fabric we're only beginning to unravel. If black holes are the universe's ultimate trash compactors, sucking in everything that crosses their path, white holes would be their cosmic opposites, spewing out matter and energy like an unstoppable fire hose. While black holes trap even light behind their event horizons, white holes defy entry. Nothing can cross inside, only erupt outward. These bizarre objects emerge as mathematical solutions to Einstein's equations, mirror images of black holes running backward in time. Imagine pressing rewind on a black hole's life cycle. Instead of collapsing inward, it would violently expel all the material it ever consumed. Some physicists speculate this isn't just theoretical. White holes could be the other end of wormholes, secret tunnels where matter entering a black hole emerges elsewhere. Or elsewhere, the mechanics get wilder when you consider their potential as time portals. If a black hole's crushing gravity slows time to a crawl near its event horizon, a white hole's explosive output might reverse the effect, accelerating timelines in its vicinity. Picture a spacetime trampoline. A black hole bends the fabric downward while a white hole kicks it upward with equal force. Bridge the two, perhaps through a wormhole, and you'd have a loop where time folds like an M. See Escher's staircase. A spaceship diving into the black hole could theoretically get hurled out of the white hole, not just in another location, but in another era. The catch: white holes are catastrophically unstable. The moment matter tries to enter, calculations suggest they'd collapse into black holes or detonate in a flash of energy. Yet there's tantalizing evidence that nature might have found workarounds. Some models propose that the Big Bang itself was a primordial white hole, a singularity violently unpacking its contents to birth our universe. Others point to gamma-ray bursts, the most energetic explosion since the cosmos began, as potential white hole signatures. In 2006, astronomers detected a mysterious flash lasting 100 seconds that matched no known supernova or collision. Dubbed the Christmas burst, its light curve aligned eerily with white hole eruption predictions. Could these flashes be the dying gasps of wormhole tunnels collapsing? The most mind-bending possibility is that white holes don't just connect points in space, they might stitch together timelines. Quantum gravity theories suggest that when a black hole evaporates via Hawking radiation, it could leave behind a microscopic white hole, essentially rebooting the ingested information into a new universe. Step through, and you might not just travel through time, but branch off into a whole new cosmic lineage where history unfolded differently. Of course, surviving the trip would require tolerating conditions hotter than supernova and navigating forces that shred atoms. But as cosmic exit signs glowing at the edge of physics, white holes remind us that the universe's recycling program might be far stranger than we dreamed. At the quantum level, particles play by rules that defy common sense. They can vanish on one side of a barrier and reappear on the other without ever crossing the space in between. This bizarre phenomenon, called quantum tunneling, is well documented in physics, allowing electrons to teleport through walls they shouldn't be able to penetrate. But what if this strange behavior isn't limited to space? What if particles can tunnel through time as well, slipping backward or forward in ways that mock our linear experience of cause and effect? This radical idea, known as temporal quantum tunneling, suggests that just as particles ignore spatial barriers, they might bypass temporal ones too. Imagine an electron not just jumping through an impenetrable wall, but arriving at its destination before it even left, like a cosmic déjà vu written into the fabric of reality. The math hints at this possibility. Quantum mechanics treats space and time as deeply interconnected, so if tunneling can happen in one dimension, why not the other? Experiments have already begun probing this frontier. In 2017, physicists at Chapman University simulated how quantum particles might behave if time were a tunnelable barrier, finding that under certain conditions, events could appear to happen in reverse order without violating causality. The key lies in retrocausality, a mind-bending concept where future events influence the past. In classic quantum experiments like the delayed choice quantum eraser, particles seem to decide their behavior based on measurements that haven't happened yet, as if the future is whispering back through time. Recent studies have taken this further, showing that entangled particles might use temporal tunneling to coordinate their states across time gaps, like synchronized dancers moving to a beat that hasn't yet played. But how could this translate to human-scale time travel? The leap from particles to people is vast, but some theorists speculate that if enough quantum systems tunneled in unison, their collective effect might ripple into the macroscopic world. Picture a futuristic device that doesn't move you through time but aligns trillions of quantum events to nudge your timeline out of phase with the rest of reality. Of course, the energy and precision required would dwarf anything we can currently imagine, and the paradox risks loom large. What happens if your tunneling attempt alters the very conditions that made it possible? For now, temporal tunneling remains a tantalizing hint scribbled in the margins of quantum theory. But every experiment probing retrocausality brings us closer to answering a haunting question. If particles can cheat time, could we one day learn their tricks? The universe seems to be keeping its options open, whispering that the arrow of time might not point as straight as we think. Rotating dust might sound like the least promising material for building a time machine, but the Van Stockholm solution proves even the humblest substances can warp reality under the right conditions. Picture an infinite, whirling cylinder of dust, not the kind you wipe off your bookshelf, but a cosmic cloud so dense and fast-spinning that it drags space-time around it like a celestial blender. In the 1930s, physicist Willem Jacob van Stockholm solved Einstein's equations for this bizarre scenario and uncovered something astonishing. Within the dust's frenetic swirl, closed time-like curves emerge naturally, like knots tied in the fabric of time itself. The mechanics hinge on frame dragging, an effect where massive rotating objects pull space-time along with them, much like a spoon stirring honey. Earth does this weekly. Experiments with gyroscopes in orbit have detected its faint influence. But Van Stockholm's dust takes it to extremes, spinning so violently that space and time twist into loops. Travel in just the right path around the cylinder, and you could find yourself returning to the same point in space and time, effectively meeting your past self. No exotic matter, no wormholes, just pure rotational energy sculpting time into a Möbius strip. Of course, the devil's in the details. For the effect to work, the dust cylinder would need near light speed rotation and densities rivaling neutron stars, conditions that would crush ordinary matter into oblivion. Even stranger, the solution demands the cylinder stretches infinitely in both directions, a physical impossibility in our finite universe. Yet as a mathematical curiosity, it's flawless, proving that time loops don't require black holes or cosmic strings. Just add enough spin and even dust becomes a temporal vortex. Critics dismiss Van Stockham's solution as a pretty equation with no real-world counterpart, but others see it as a clue. Certain dense, rotating galaxies or quasars might approximate the conditions on cosmic scales, with their sprawling arms potentially creating microscopic CTCs in their cores. And if advanced civilizations could engineer ultra-dense, fast-rotating rings, perhaps using collapsed matter or controlled plasma vortices, they might stumble onto a simpler path to time travel than wrestling with black holes. The real lesson here isn't about dust, it's about rotation's hidden power. From spinning neutron stars to Van Stockham's hypothetical whirlwind, the universe keeps whispering that if you want to bend time, sometimes you just need to twist space hard enough. The trick is surviving the spin. Einstein's twin paradox is one of the most startling demonstrations of time dilation, where one sibling rockets off into space at near light speed and returns to find their Earth-bound twin has aged decades while they've barely aged at all. But this isn't just a thought experiment, it's a mathematical certainty woven into the fabric of relativity. Let's break it down with real numbers. Suppose one twin boards a spaceship accelerating to 99.9% the speed of light, a velocity we've nearly achieved in particle accelerators, and embarks on a 5-year round trip to a nearby star. From their perspective, time passes normally, 5 years of meals, sleep cycles, and star charts, but back on Earth, relativity warps the numbers dramatically. At that speed, time slows by a factor of roughly 22. While the traveling twin experiences 5 years, Earth clocks tick off 110. The astronaut returns to a world where their sibling is elderly, their childhood friends are gone, and pop culture has moved on to genres they don't recognize. The math behind this is both elegant and unsettling. Time dilation stems from Lorentz transformations, equations that describe how time and space stretch at relativistic speeds. Plugging in the numbers reveals a nonlinear relationship. At 90% light speed, time slows by about 2.3 times, pushed to 99%, and the factor jumps to 7. At 99.99%, a speed some scientists believe could one day be possible for spacecraft using antimatter propulsion. A single year for the traveler equals 71 on Earth. This isn't science fiction, it's the universe's own timekeeping mechanism, indifferent to human expectations. Practical hurdles make this kind of time travel a one-way trip to the future, with no return ticket to the past. Accelerating a human to such velocities would require energy surpassing global annual output, and surviving the G-forces would demand technology we can scarcely imagine. Even ignoring those challenges, the cosmic speed limit ensures you can't reverse the effect. There's no slowing down time on Earth to catch up. The asymmetry is baked into relativity's equations. Yet the implications are profound. A civilization mastering near light speed travel could effectively leap millennia into the future, bypassing wars, plagues, or even the heat death of stars. What's often overlooked is how this reshapes our view of time itself. We think of it as a river flowing uniformly for everyone, but relativity reveals it's more like a network of streams, each moving at different speeds depending on gravity and velocity. GPS satellites already account for this, adjusting their clocks to sync with Earth's surface. On a human scale, the differences are minuscule seconds over a lifetime, but they prove the effect is real. The twin paradox just scales it up, showing that with enough speed, time becomes a negotiable dimension. The ultimate twist, from the astronaut's perspective, Earth is the one moving at near light speed relative to their ship. In their frame of reference, it's Earth's clocks that crawl. This mutual time dilation isn't a contradiction but a core tenet of relativity. There's no universal now. Both experiences are equally valid, and only the reunion, the moment the twins compare clocks, reveals who truly aged slower. It's a cosmic game of musical chairs where the music is time itself, and the last one sitting is the youngest. For all its strangeness, velocity-based time dilation is the only form of time travel indisputably allowed by physics. Wormholes and warp drives may dance at the edges of theory, but astronauts on the International Space Station already return home ever so slightly younger than if they'd stayed grounded. The effect is tiny microseconds per year, but it's a whisper from the universe that time is fluid, and the future is always waiting at the right speed. While velocity-based time dilation twists the clock for astronauts racing through space, gravity performs its own slow-motion magic on time, and nowhere is this more extreme than near a black hole. Picture a planet like Interstellar's Miller's World, orbiting so close to a supermassive black hole that 1 hour on its surface equals 7 years back on Earth. The movie's depiction wasn't just Hollywood flair, it was rooted in real physics. Einstein's general relativity tells us that gravity doesn't just pull on objects, it tugs on time itself, stretching seconds like taffy in a cosmic funhouse. Stand near a black hole's event horizon, and your watch would tick agonizingly slow compared to someone watching from a safe distance. The math behind this is both elegant and daunting. Gravitational time dilation stems from the warping of spacetime. The deeper you sink into a gravity well, the more time slows. On Earth, the effect is minuscule but measurable. A clock at sea level lags behind one on a mountaintop by microseconds per year. But crank up the gravity and the numbers explode. Near a black hole with 10 times the sun's mass, time dilation could stretch 1 minute into a decade for a distant observer. The closer you hover to the event horizon, the more extreme the slowdown until, at the point of no return, time appears to freeze completely from the outside. To a watching astronaut, your final approach would seem to stretch into eternity, your image redshifted into oblivion as the black hole's gravity steals even the light from your body. What's wild is that for you, time would feel normal. Step across the horizon, and your wristwatch keeps ticking at its usual pace. It's the universe outside that accelerates into fast forward. This asymmetry creates a bizarre disconnect. While you might experience minutes falling inward, the cosmos beyond could blaze through millennia in the same span. Theoretically, if you could skim the horizon and escape, perhaps using some futuristic propulsion, you'd catapult into a future where civilizations rose and fell during your brief absence. Black holes aren't the only players in this temporal distortion. Neutron stars, the dense corpses of exploded suns, also twist time noticeably. Spin one fast enough, and its crushing gravity paired with rapid rotation could create frame-dragging effects that loop time back on itself. Even our humble sun bends clocks slightly. GPS satellites must account for both the velocity-based slowdown of their orbit and the gravitational speed-up from being farther from Earth's mass. Leave either factor uncorrected, and navigation systems would fail within hours. The takeaway: gravity doesn't just shape space, it sculpts time, and the universe has been quietly proving it for billions of years. Whether through the gentle tug of a star or the ruthless grip of a singularity, time is always negotiable, always bending to the will of mass and motion. The real mystery isn't whether this happens, but how far we might one day push the limits and what futures we could glimpse by surfing the gravitational tides. Eternalism flips everything we think we know about time on its head. Instead of a flowing river where the present slips into the past while the future rushes toward us, Picture the entire universe as a frozen block, a four-dimensional sculpture where every moment, from the Big Bang to the heat death of stars, exists simultaneously. This is the block universe theory, and it treats time like just another direction you could move through, no different than left, right, up, or down. In this view, your birth, your first heartbreak, and even your last breath aren't past, present, or future events. They're fixed coordinates in spacetime, like cities on a map. This isn't just philosophical musing, it's baked into Einstein's relativity. When he merged space and time into a single continuum, he erased the idea of a universal now. What's present for you might be past or future for someone moving at a different speed or caught in a stronger gravitational field. The block universe takes this further, declaring that all those perspectives are equally real. Think of it like a DVD. The entire movie exists on the disc, but your consciousness is the laser reading one frame at a time, creating the illusion of motion. So what does this mean for time travel? If the block universe is real, journeying through time wouldn't be about changing history. It'd be about navigating to a different part of the sculpture. You wouldn't rewrite events any more than driving from New York to Los Angeles erases one city to create the other. This neatly sidesteps paradoxes. Your future self was always there in the block, just as your past self still is. The catch: free will becomes a cosmic mirage. Every choice you'll ever make is already etched into spacetime, leaving you more like a reader flipping through a finished book than an author penning the story. Some physicists argue this is the only way time travel could work without imploding logic. Want to visit ancient Rome? The block universe says Rome never ended. It's still out there, a slice of the space-time loaf you could theoretically slice into. The challenge is finding the right knife. Wormholes or cosmic strings might act as shortcuts between distant points, but even then, you're not going back. You're just taking a diagonal path through the block. Critics counter that eternalism feels bleak, reducing life to a pre-recorded film. But supporters find solace in its elegance. No lost moments, no true endings, just the universe's grand tapestry waiting to be explored. Whether it's true or not, the block universe forces us to confront a haunting question. If time is an illusion, what else might be? The bootstrap paradox is like a cosmic magic trick where the rabbit doesn't just disappear, it was never in the hat to begin with. Imagine a time traveler hands young Beethoven a stack of sheet music containing his own future symphonies, which he then copies and publishes as his original work. Centuries later, those same compositions are sent back to him, completing an endless loop with no true starting point. Where did the music really come from? The universe shrugs. It just is a perfect circle of causality with no creator, no first draft, just an idea trapped in its own echo. This isn't just a quirky thought experiment. The bootstrap paradox forces us to confront whether information or even physical objects can exist without origin. Picture a scientist in the 23rd century building a time machine using blueprints they found in a museum, blueprints that turn out to be schematics they themselves will later send to the past. No one ever invented the design. It's a relic without a birth certificate, forever cycling through time like a celestial boomerang. The paradox gets thornier with knowledge. What if a modern physicist reads equations from an ancient text, only to later realize those equations only existed because they themselves traveled back and taught them to the ancients? The equations have no author, only messengers. Some theorists argue the paradox reveals a chilling truth. If time loops are possible, creation might be an illusion. The universe could be littered with bootstrap artifacts, objects, songs, even people caught in infinite causal loops. Others propose quantum mechanics might offer an escape hatch. In the many worlds interpretation, every loop could spawn a new timeline where the information appears spontaneously, sidestepping the need for an origin. But the most unsettling possibility, that bootstrapping isn't a bug in time travel's code, it's a feature, hinting that some things were meant to exist outside linear causality. their very existence a riddle wrapped in the fabric of spacetime. The next time you hum a melody that feels eerily timeless, ask yourself, could it be a stray note from a symphony that no one ever truly wrote? Parallel timelines offer a daring escape from the suffocating grip of paradoxes. What if every decision you make doesn't rewrite history but branches it? This is the core idea behind multiverse time travel, a radical departure from single timeline models where changing the past overwrites the present like a palimpsest. In a branching universe, stepping on a butterfly in the Cretaceous wouldn't erase your future. It would spin off a new reality where dinosaurs still rule, while your original timeline continues untouched. The grandfather paradox melts away because you're not erasing your ancestry, you're just switching tracks to a parallel line where it never existed. The mechanics hinge on quantum superposition scaled to cosmic proportions. Every quantum event, a particle spinning left or right, unfolds both ways, splitting reality into versions where each outcome happens. Extend this to human choices and every what if becomes a somewhere. Miss a train in one world, there's another where you caught it and another where the train derailed. Time travel in this framework isn't about altering events, it's about hopping between these pre-existing branches. Think of it like a subway system with infinite routes. Your past self is still on the original line, living the life you remember, while your time-traveling self steps onto a fresh track where the rules are yours to bend. The allure of parallel timelines isn't just in dodging paradoxes, it's in the sheer creative freedom. Want to see a world where the Library of Alexandria never burned? There's a timeline for that. Curious about a 21st century where Nikola Tesla's wireless power grid revolutionized energy? It's out there. The multiverse becomes a playground where history's unmet potentials play out in full, no causality police in sight. But this freedom comes with a haunting caveat. Once you jump, you can't go home. Your original timeline churns forward without you, forever out of reach. Every leap is a one-way trip into the unknown. Critics argue this turns time travel into a glorified dimension-hopping fantasy, stripping away the emotional weight of changing or failing to change your own past. Others counter that it's the only model that reconciles time travel with quantum mechanics without imploding logic. After all, if particles can occupy multiple states, why not entire histories? The debate rages, but one thing's certain. In a multiverse, time isn't a thread to rewind. It's a tapestry of infinite threads, each vibrating with its own version of now. Whether that's liberating or lonely depends on how tightly you cling to the idea of a singular, shared reality. Quantum mechanics has a habit of turning our everyday logic inside out, and nowhere is this more apparent than in the eerie phenomenon known as quantum retrocausality, where the future seems to whisper back to the past. Imagine flipping a coin and watching it land only to realize its outcome was somehow influenced by a decision you haven't even made yet. This isn't science fiction. It's a real possibility emerging from quantum experiments that suggest particles might not just move through time but negotiate with it. At the heart of this madness is the idea that quantum systems can flip time states, behaving as if cause and effect are playing a game of tug-of-war where both teams pull at once. Take the infamous delayed choice quantum eraser experiment. Photons fired through a maze of detectors seem to decide whether they behaved as particles or waves after they've already been measured, as if their past is being rewritten by future observations. It's like mailing a letter that changes its content based on whether the recipient decides to open it. Some interpretations suggest these particles aren't just probabilistic but retrocausal, with future interactions reaching back to mold their earlier states. This flips the script on time's arrow, implying that quantum reality isn't a straight line but a tangled web where events can resonate backward like ripples in a pond flowing upstream. The implications are staggering. If quantum systems can blur the line between past and present, could larger systems, even humans, ever harness this effect? Theorists speculate that entangled particles might act as anchors for temporal flipping, their synchronized states bypassing linear time entirely. Picture a network of quantum computers so finely tuned they could send computational hints backward, solving problems before they're fully posed. Or consider a hypothetical time capsule that doesn't just store information but uses quantum loops to update its contents from the future. Of course, scaling this from particles to people is a leap as vast as the Big Bang itself. The quantum world thrives on uncertainty, while our macroscopic reality clings to causality like a life raft. Yet recent lab experiments keep nudging the door open. In 2020, physicists demonstrated that certain quantum circuits could optimize their own past configurations, effectively learning from outcomes that hadn't yet occurred. It's as if the universe left a backdoor in its code, and we're just starting to peek through the keyhole. The real controversy lies in what this means for free will. If the future can tweak the past, are choices ever truly ours, or just echoes of events we haven't lived yet? Some argue retrocausality doesn't erase agency, it just redefines it, casting decisions as threads woven through time's tapestry rather than isolated moments. Others counter that if time is this fluid, reality might be less a sequence and more a symphony, with every note, past, present, and future playing at once. One thing's certain, quantum time flips don't just challenge our understanding of clocks and calendars. They force us to ask whether time itself is a construct, a convenience our brains invented to make sense of a universe far stranger than we ever imagined. And if particles can dance backward through time, who's to say we won't one day learn the steps? Negative energy sounds like something out of a fantasy novel, but in physics, it's a very real and very bizarre ingredient that might hold the key to unlocking time travel. Unlike the energy we're familiar with, which powers stars and light bulbs, negative energy has the opposite effect. It repels rather than attracts, acting like anti-gravity. This strange property makes it the perfect theoretical glue to hold open wormholes or power warp drives, preventing them from collapsing under their own gravity the instant they form. Think of it like trying to keep a tunnel open in wet sand. Ordinary matter would crumble, but negative energy could act as cosmic scaffolding, propping up the walls against the crushing weight of spacetime itself. The Casimir effect offers a tantalizing glimpse of how negative energy might exist in nature. Take two uncharged metal plates and place them impossibly close together in a vacuum. At these microscopic distances, quantum fluctuations, the constant flickering of particles in and out of existence, get squashed. Normally, these fluctuations balance out, but between the plates, certain wavelengths are excluded, creating a pressure imbalance. The result, the plates are pushed together by an invisible force, and the space between them effectively holds less energy than the surrounding vacuum, a localized patch of negative energy. It's a tiny effect, barely enough to nudge atoms, but it proves the principle. Under the right conditions, the universe can produce energy densities that defy common sense. Scaling this up to stabilize a wormhole would require unimaginable amounts of negative energy, far beyond what the Casimir effect can currently generate. Some calculations suggest you'd need the equivalent of Jupiter's mass converted into exotic matter just to hold open a tunnel 1 meter wide. And that's not even accounting for the radiation feedback problem, where particles looping through the wormhole could amplify into an infinite energy burst, vaporizing the entire structure. Yet the tantalizing possibility remains. Quantum field theory allows for negative energy densities in short bursts, and some models suggest advanced civilizations might harness these fleeting fluctuations like a surfer riding quantum waves. The irony is delicious. To master time travel, we might need to harness energies that seem to defy the very laws of physics. Whether through Casimir cavities scaled to cosmic proportions or yet undiscovered quantum phenomena, negative energy stands as both a hurdle and a beacon, a signpost pointing toward a universe far stranger than we've dared to imagine. Groundhog Day and Edge of Tomorrow make time loops look like cosmic glitches, amusing at first, then deeply unsettling as characters relive the same moments endlessly. But fiction's take on temporal déjà vu isn't pure fantasy. It's borrowing from real physics' most mind-bending ideas. Take closed timelike curves, those theoretical pathways where time bends back on itself like a Möbius strip. While Hollywood simplifies loops into character arcs, the science behind them is far stranger. A real time loop wouldn't just reset your surroundings like a movie set. It would stitch the end of your journey seamlessly to the beginning, with no jumps or cuts, leaving you unaware you're trapped until patterns emerge. Quantum mechanics adds eerie parallels to fictional loops. In the quantum realm, particles can enter time-like states where their behavior mirrors a system stuck in repetition. Experiments with entangled particles show behaviors that, if scaled up, might resemble a microscopic version of Groundhog Day events recurring until a specific outcome collapses the cycle. Some interpretations suggest the entire universe could be in a quantum loop, replaying variations of itself until certain conditions are met. It's a far cry from Bill Murray's Weatherman, but the core idea, repetition as a mechanism for change, echoes between lab equations and screenplays. Yet fiction often misses the cruel elegance of real temporal cycles. In films, characters retain memories from each loop, using them to grow or solve puzzles. But most physical models of time loops, like Gödel's rotating universe or Tipler's cylinder, would erase your awareness of repetition. You wouldn't learn from each cycle because, from your perspective, time would flow normally. The loop is only visible from outside, like watching a train circle a track while passengers inside feel they're moving straight ahead. This raises a haunting question. If we're in a loop right now, how would we ever know? The exchange between science and fiction isn't one-sided. Physicists like Kip Thorne admit sci-fi narratives, from H.G. Wells to Interstellar, often inspire new research angles. The bootstrap paradox, a headache for theorists, became mainstream after films like 12 Monkeys weaponized its logic. Even the term time loop entered scientific discourse because storytellers needed shorthand for phenomena that equations described less vividly. Meanwhile, fictional tropes like loop-breaking conditions have nudged physicists to explore whether quantum measurements or entropy thresholds could destabilize real-world CTCs. What both realms agree on, loops aren't just about repetition, they're about inevitability. Whether it's a film character doomed to repeat a day until they become selfless, or a particle cycling through states until it reaches equilibrium, the message is the same. Time, when twisted into a circle, becomes a teacher. The difference is that science's loops are in different classrooms, where the lesson might be written in math we don't yet understand, not scripted for emotional payoff. Perhaps that's why we keep weaving stories about breaking free, because reality's loops offer no guarantees, just the faint hope that somewhere in the spin, a pattern emerges. Consciousness might be the ultimate time machine, not because it bends space-time, but because it could rewrite the rules of how we experience time altogether. Most of us perceive time as a straight line, an unbroken thread stretching from memory to anticipation. But what if that's just the brain's clever illusion? Some theories suggest consciousness doesn't operate in strict chronological order. Instead, it stitches together moments like a film editor splicing scenes out of sequence, creating the seamless flow we take for granted. This idea isn't just philosophical speculation. It's rooted in cutting-edge neuroscience and quantum physics, challenging everything we assume about past, present, and future. Take the Orch-or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hamroff. They argue that consciousness arises from quantum vibrations in microtubules, tiny protein structures inside brain cells. These vibrations don't just process information, they might also dance along the edge of classical and quantum reality, where time's arrow isn't so rigid. In this view, the brain isn't just observing time, It's participating in its creation, weaving moments together in ways that could allow for non-linear perception. Imagine a pianist playing a complex piece. Their fingers don't move note by note in perfect sequence, but anticipate chords and rhythms ahead of the beat. Consciousness, according to Orchor, might work similarly, tapping into a symphony of quantum states that exist outside ordinary time. This gets even wilder when you consider phenomena like time dilation in near-death experiences or psychedelic states. People report lifetimes flashing before their eyes in seconds, or hours stretching into what feels like eternity, a single moment fracturing into infinite depth. These aren't just hallucinations, they could be glimpses of consciousness untethered from the brain's usual timekeeping. Studies on psilocybin and DMT show these substances drastically alter temporal perception, slowing subjective time to a crawl or erasing the sense of sequence entirely. If chemicals can warp our internal clocks so easily, it hints that linear time might be more of a biological convenience than an immutable law. Then there's the time slip phenomenon, anecdotal but persistent accounts of people briefly experiencing past or future events as if physically present. A tourist turns a corner in modern Paris and suddenly sees Marie Antoinette's carriage rumbling past. A hiker in the Scottish Highlands swears they glimpsed a medieval battle raging in the mist. While skeptics dismiss these as tricks of memory or imagination, some theorists propose they could be moments when consciousness briefly decouples from the brain's default time filtering mechanisms, like a radio picking up signals from a distant station. The implications are staggering. If consciousness isn't bound by linear time, could we train it to navigate temporal layers like pages in a book? Meditation traditions already speak of timeless states where past traumas heal and future potentials crystallize not as metaphors but as direct experiences. Advanced practitioners in disciplines like Tibetan Dream Yoga claim to consciously explore alternate timelines or foresee events with uncanny accuracy. Modern experiments with precognition and presentiment, where subjects unconsciously react to stimuli seconds before they occur, lend eerie support to these ancient ideas. Of course, mainstream science remains cautious. Orchor is controversial, with critics arguing quantum effects would decohere too quickly in the warm, wet environment of the brain. Time slips and precognition lack reproducible lab evidence, leaving them in the realm of intriguing anomalies. Yet the sheer persistence of these phenomena across cultures and epochs suggests something deeper at play. Whether it's quantum vibrations, untapped neural architectures, or undiscovered physics, one thing is clear: time as we perceive it might be the tip of an iceberg, with consciousness itself shaping the unseen depths below. Perhaps the most humbling thought: if time is more fluid for consciousness than for clocks, we might already be time travelers, our minds subtly surfing the currents of past and future, mistaking the ride for solid ground. The real question isn't whether we can build a machine to navigate time, but whether we've been wearing the mechanism inside our skulls all along. Dark matter is the universe's ultimate ghost story, an invisible, enigmatic substance that outweighs all visible matter 5-1, yet refuses to interact with light or any known force except gravity. It's the cosmic scaffolding holding galaxies together, the unseen hand shaping the cosmos. But what if its influence goes deeper than just bending the paths of stars? Some theorists speculate dark matter could be the missing ingredient in our time travel recipe, a secret architect of spacetime's hidden contours. The idea hinges on gravity's intimate dance with time. Einstein showed us that massive objects warp spacetime, slowing clocks in their vicinity. Dark matter, despite being invisible, exerts gravitational pull just like ordinary matter, and there's a lot of it. Imagine a region of space densely packed with dark matter, far more concentrated than the diffuse halos we typically observe. Its gravitational field might curve spacetime so severely that time itself stutters, creating pockets where clocks tick at radically different rates. Unlike black holes, these dark matter time wells wouldn't come with event horizons or lethal tidal forces, just quiet, invisible eddies in the fabric of reality. One tantalizing possibility involves dark matter filaments, the wispy threads theorized to connect galaxy clusters across the cosmos. If these filaments contain ultra-dense knots, they could function like natural time dilation highways. A ship riding the gravitational field of such a knot might experience hours while decades pass elsewhere, effectively catapulting travelers into the future. There's even speculative math suggesting certain dark matter configurations could twist spacetime into closed timelike curves, those elusive loops where time folds back on itself. The catch: we've never detected dark matter directly, let alone mapped its structure well enough to spot these hypothetical knots. Critics rightly point out the gaping holes in the idea. Without knowing what dark matter is, whether it's WIMP, actions, or something even stranger, we can't say how it might interact with spacetime beyond basic gravity. Plus, the universe's dark matter seems too smoothly distributed to form the dense clusters needed for noticeable time warps, but the math leaves room for surprises. If a fraction of dark matter clumps into dark stars or other exotic structures, their cumulative gravity could bend time in ways we're only beginning to model. The most intriguing twist comes from quantum theory. Some dark matter candidates, like sterile neutrinos, might interact weakly with unknown quantum fields that permeate space. If these fields couple to spacetime itself, dark matter could act like a cosmic dial, tweaking the stiffness of time's fabric in ways ordinary matter can't. Picture a labyrinth where certain walls are invisible. Dark matter might be the unseen architect building temporal shortcuts right under our noses. For now, dark matter's role in time manipulation remains a dazzling what if. But the universe has a habit of being stranger than we imagine. Every time we've dismissed an idea as too outlandish — black holes, gravitational waves, quantum entanglement — nature has proven us wrong. Whether dark matter holds the key to time travel or not, its mysteries remind us that the cosmos is still writing its rulebook, and some of its most thrilling chapters may be hiding in the dark. Entropy is the universe's strictest accountant. It keeps track of every speck of energy, ensuring the books always tilt toward chaos. The second law of thermodynamics states that in any closed system, disorder must increase over time, an irreversible march toward equilibrium we call time's arrow. Sandcastles crumble, coffee cools, stars burn out, all because entropy demands it. But what if time travel isn't just about bending space-time? What if it's about outsmarting this cosmic rulebook, finding loopholes to reverse entropy's grip on reality? At first glance, thermodynamics seems like the ultimate buzzkill for backward time travel. If time's arrow points the way it does because of increasing entropy, reversing time would mean unscrambling eggs, unburning stars, and reconstructing shattered vases from dust. Yet physics doesn't outright forbid localized decreases in entropy. It just requires a greater increase elsewhere to balance the books. Your freezer does this every day, creating a pocket of order by expelling heat into your kitchen. Scale this up, and you might imagine a time machine that temporarily reverses entropy in its immediate vicinity, creating a bubble where time's arrow flips while the wider universe pays the thermodynamic price. Quantum mechanics offers a glimmer of hope here. At microscopic scales, particles occasionally exhibit entropy dips, where disorder momentarily decreases without breaking any laws. These fluctuations are fleeting and tiny, but in theory, if you could orchestrate trillions of them in perfect sync, perhaps using quantum entanglement or exotic states of matter, you might stitch together a macroscopic entropy reversal. Picture a supercomputer coordinating a symphony of atoms, coaxing them to rewind their states in unison, effectively rolling back time inside a controlled field while the outside world marches forward. The catch: even if you could reverse entropy locally, you'd still face the grandfather paradox in a new guise. A time traveler's presence in the past would introduce energy and information from the future, potentially creating contradictions. Unless, as some theories suggest, the act of time travel itself generates compensating entropy like a cosmic surcharge to keep the overall balance sheet intact. Imagine stepping into the past and feeling an inexplicable heat wave ripple through the air around you, as if the universe is settling its thermodynamic debt. Some physicists argue that black holes might already be playing this game. Their event horizons trap entropy, hiding it from the rest of the universe, while Hawking radiation leaks energy back out in a messy, randomized form. Could a sufficiently advanced civilization harness this process, using black holes as entropy sinks to create temporal eddies where time flows backward? The math is speculative, but the possibility lingers, a reminder that the universe's rules are more flexible than they seem. The ultimate twist: entropy might not be time's master, but its collaborator. Recent work in quantum gravity suggests that entropy and spacetime are deeply entangled, two sides of the same cosmic coin. If true, manipulating one could inherently alter the other, opening paths to time travel we've yet to imagine. The second law wouldn't be a wall, just a door waiting for the right key. Until then, every melting ice cream cone is a quiet testament to the universe's stubborn forward march, and every fleeting quantum fluctuation, a whisper that the past might not be as lost as it seems. Simulation theory throws open the doors to a possibility so radical it redefines our entire concept of time travel. What if our universe isn't fundamental reality, but an advanced digital construct? In this scenario, the passage of time might not be the steady unfolding of physical events, but the sequential processing of computational steps, like frames rendered in a hyper-advanced simulation. Time travel, then, wouldn't require wormholes or warp drives, just the ability to pause, rewind, or access the source code governing our existence. Think of it like opening the debug menu in a video game and tweaking the variables that dictate when and where events occur. This idea isn't just speculative fiction. Philosophers like Nick Bostrom have seriously argued that if civilizations inevitably create ancestor simulations, hyper-realistic digital recreations of their past, the statistical likelihood we're living in the original universe is vanishingly small. If true, it reshapes time travel from a physics problem to a matter of hacking the system. A simulated world could have save points, backups, or even cheat codes that allow entities with admin privileges, whether future humans or the simulation's architects, to jump between eras as effortlessly as scrolling through a timeline. The Mandela effect, those eerie collective false memories where people swear historical details have changed, might not be glitches in human cognition but literal patches applied to the simulation, subtly editing past events without wiping participants' memories clean. But here's where it gets ethically fraught. If time travel is possible within the simulation, why haven't we encountered time travelers? One chilling answer: the programmers have rules against it. Imagine a cosmic terms of service agreement that forbids meddling with historical timelines to preserve the simulation's integrity, or worse, to maintain the illusion of free will for its inhabitants. Ethical debates would rage over whether allowing time travel would turn reality into a playground for the privileged few, where those with access to the code could rewrite history for their benefit. Would altering past events be seen as a harmless experiment or a form of digital colonialism, erasing entire branches of perceived experience for simulated beings who, from their perspective, are as real as anything could be? The moral quandaries deepen when you consider consent. If we're simulated, do we have a right to know if our past is being edited? Would revealing the existence of time travel break the simulation's immersion, causing existential panic, or inspire its inhabitants to reverse engineer their own escape? Some theorists propose that glitches in quantum experiments, like particles behaving differently when observed, might be artifacts of the simulation's rendering engine struggling to maintain consistency when players peek behind the curtain. Simulation theory doesn't just offer a new mechanism for time travel, it reframes the entire debate. Suddenly, paradoxes like the grandfather loop aren't physics problems but programming challenges. Need to avoid a contradiction, the simulation could spawn a parallel instance where the altered timeline plays out, or it might simply reset the affected variables behind the scenes. Even the flow of time itself could be an illusion, with all moments existing simultaneously in the simulation's memory banks, waiting to be accessed like files in a folder. Yet for all its elegance, the theory leaves us with a haunting uncertainty. If we ever gain the power to rewind or fast-forward time, would we be the heroes of our own story, or just NPCs in someone else's experiment, chasing freedoms that were never really ours to claim? The answer might depend on whether the architects of our reality left the debug menu unlocked, or if they're watching us try to find it. From the mind-bending curves of general relativity to the ghostly whispers of quantum entanglement, our journey through time travel theories has revealed a cosmos far stranger than fiction. Einstein's spacetime bends like taffy near black holes, while quantum particles flirt with retrocausality, seeming to rewrite their own histories. Wormholes dangle the promise of cosmic shortcuts, and dark matter lurks as a potential architect of hidden temporal eddies. Some ideas, like the Alcubierre warp drive, tease the edges of possibility with math that refuses to say never. Others, like Novikov's self-consistency principle, turn paradoxes into puzzles with built-in solutions. The sheer diversity of these theories, 30 and counting, proves one thing: humanity's obsession with time isn't just fantasy. It's a frontier. For all our clever equations and thought experiments, time travel remains locked in the realm of maybe. Yet that's where science thrives, not in certainty but in curiosity. Every failed experiment, every debunked claim, even the wildest hypotheses that fizzle out, they all push the boundaries of what we understand. The universe doesn't owe us time machines, but it does reward those who dare to ask what if. Whether it's a rotating cylinder of dust or a quantum fluctuation echoing backward through time, each theory is a torch lighting another corner of the unknown. So here's the real question: which of these ideas sparks your imagination? Are you Team Wormhole, holding out for a cosmic subway through the ages? Or do you bet on quantum retrocausality, where the future tugs on the strings of the past? Maybe you're captivated by simulation theory, where time travel is just a line of code away. Drop your favorite theory in the comments. Let's keep the conversation hurtling forward. After all, the next breakthrough might start with a single what if from someone